Alright friends, so here we are doing the exact same thing as before, except instead of velocity, we're doing acceleration. Again, this is this lovely thing where we've assumed that the ddt of I hat is not changing. We're just assuming we have a, okay, I know you don't care, but just pretend you care for like 12 seconds. It'll make me feel like I taught you something. So the idea would be that if we had r is equal to x I hat, or let's just say, because now we're in v. So if we have velocity is equal to some x velocity component I hat, velocity component j hat, velocity component k hat, we can take the ddt of the whole thing, this should have a hat on it, and then we get acceleration. Now in theory, dvx dt I hat plus vx di hat dt, and then I'm just going to write the whole thing out for you. dvy dt j hat plus vy dj hat dt, and then plus dv, I can't spell, dvz dt k hat plus dk hat dt times vz, right there. Okay, but again, we're assuming that our I hat, j hat, k hat don't move. We're in a non-rotating plane, so these all go to 0, and your book doesn't tell you that. But this is actually a huge deal, and this is the difference between, like, okay, so like, you know when you look at Mars or the moon? No, Mars. Okay, so if you're here looking at Mars, you know how we go around Mars, or the moon, the sun, and then Mars goes around the sun? Well, if you think that we go around, or that we're the center of the universe, then Mars does this. Okay? And those, they used to call them epicycles. If you really want to go off into the internet craziness, look up epicycles for Mars. And you get Martian epicycles when you don't realize that you have a rotating plane. So back when we didn't think we had a rotating plane and we thought we were the center of the universe, we had all this weird stuff going on because we didn't realize that in fact dk hat dt, dj hat dt, and di hat dt were not in fact 0. But for the purposes of an apple falling from a tree, they are, and we're able to stick with just the acceleration is the ddt of each of the components of the velocity. And again, the idea is that each of those components of velocity are entirely independent. Oops, that's supposed to be a k hat. Are entirely independent of each other. See how they're not depending on each other? The x stays in the x line, the y stays in the y line, and the z stays into the z line. And that's really the big thing that we want to be paying attention to here. Okay, so let's look at this. So a particle has this velocity. What is the acceleration function? So essentially, really all you need to do on this is remember that acceleration is d velocity dt. So we're just going to dt this vector, 5t I hat plus t squared j hat minus 2t cubed k hat. So we've got the acceleration vector is 5 I hat plus 2t j hat minus 6t squared k hat. So don't overthink this. You just literally take the derivative of it, and then you've got your, oh, that's the same thing written there. You just literally got that. And then if you want to know, well, what is it at 2 seconds, you just plug in 2. Okay? Okay, same thing for the position function. If you have the position function r being equal to 10t minus t squared I hat plus 5t j hat plus 5t k hat. Then if you want the velocity, it's the ddt, so 10t minus 2, or sorry, 10 minus 2t. 10 minus, see, this is why you need to know calculus before you come to this class. 10 minus 2t I hat plus 5 j hat plus 5 k hat. And then acceleration, I feel like we've already done this. Minus 2 I hat plus, well, 5, the ddt of 5 is 0. And then the ddt of 5 again is 0. So we just have acceleration in the I hat direction. Make sense? Okay. So don't overthink this. You're just literally taking derivatives. Anytime you get confused about what's going on, you can always go back to the basic definition that velocity is dx dt. Now, they also call it dr dt. R just means it's like the general position. So dx would just mean if you're in one dimension. So I guess that's, so whenever we said dx dt, that was kind of assuming this was one dimension. If we have two or more dimensions, we call it dr dt, but don't let that r freak you out. It's just a normal r, just means position. Please don't let it freak you out, because that's the kind of thing that would have me in stitches for a week. And then acceleration is dv dt. And in 1D, just regular acceleration was regular velocity dt. Okay, so the only reason that this one is x and this one is r is because in x we're just doing one dimension, so we just pretend the dimension is always x, so we're just going back and forth and back and forth. R is supposed to be representative of the idea that we could be in this, x, y, z coordinate plane, if that makes sense. Cool? Sort of? Sort of getting somewhere? Okay. Okay. So now the whole idea with constant acceleration is just, maybe obviously, if you take the integral, that you get that 1/2 at squared thing that we've talked about before. But again, this shouldn't become anything new or exciting because we've already done this. But again, anytime your brain goes, I don't know what's going on, go back to the basics, take the integral, and you'll always, always, always have it right. But 100%, never, never, never can you use these unless only when acceleration is constant, and that pretty much is only whenever it's like gravity, or it'll be something like, they apply the brake so that they're decelerating at a constant rate of 3 meters per second squared or something like that. But in real life, the only time you might see constant acceleration is with gravity, and even then it's not officially like that. It's just when we assume the cow is spherical. So these are wonderful equations and they're fine, but they're only valid when acceleration is constant, and any other time you a trillion gajillion percent need to be going back to the definition of a derivative and an integral. Okay, so let's see what else is going on here. Doop-de-doop-de-doo. Okay, so interesting. Velocity, what are the x and y components? Okay, so there's a skier and he's moving with this velocity of 2.1 meters per second acceleration down a slope. And it wants to know, here's her initial position and her initial velocity. What are her x and y components as a function of time? Okay, so this is going to be kind of like your x naught, like your initial position. So x naught would be 75. Y naught would be negative 50. Like that's your initial positions, right? Your initial velocity, I guess, x at 0? I don't know how you want to write that. Whatever makes you happy is 4.1, and initial velocity in the y direction is negative 1.1. Okay. So you can either use the memorized equations or you can go back to base principles. It's telling us that we have an acceleration at a slope of 15 degrees of 2.1 meters per second squared. Okay, so the two components, the sign is the opposite, so this is going to be 2.1 sine 15, and the adjacent is 2.1 cosine 15 degrees. So if I was going to write a vector describing the acceleration, it's going to be 2.1 cosine 15 degrees I hat and then minus 2.1 sine 15 degrees. You can't see what I'm doing. J hat meters per second squared. And I can put real numbers on that. 2.1, can't spell. 2.1, doopy-doopy-doo, cosine 15, and then 2.1 sine 15. Okay. Oh, I'm in radians. Whew. I was like, why is it negative? Mode, radian, degrees. Okay, let's try this again. Oops, that's not what I meant either. I meant to go up here. Cosine and sine. Let's delete the bad ones. Clear and clear. Okay, so I have sine and cosine in degrees, so, well, that's important. Okay, so about 2.03 and 0.544. 2.03 negative 0.544. Okay, is that right? I like it. Okay, so now I want to treat each of these separately. So I can express the x position in terms of t as 1/2 at squared. I'm just going to write it like this for the moment. At squared plus v naught in the x direction, t plus x naught. Now this is where you run into, you get a whole lot of subscripts because technically this is acceleration in the x direction. Okay, so 1/2 a in the x direction, t squared, plus v naught in the x direction, t, plus initial position in the x direction. The y position is 1/2 a y direction, t squared, plus v naught in the y direction, t, plus initial value in the y direction. Okay, so that's how that kind of works together. Now, in my case, I know that this acceleration in the x direction is 2.03 t squared. V naught was the 4.1, and the x naught was 75, and y at t, 1/2 negative 0.5. See how that negative just goes in there? And that's why I don't like to memorize these formulas with the negatives already in it. Just apply the negative if it happens to be negative. And this is kind of good because it forces you to know what's going on. Like look, it's slowing down. It's negative acceleration kind of a thing. Okay. So we've got these. So those are our positions as a function of time. If I wanted to get the velocities as a function of time, so the velocity of x as a function of time, t squared times that would just be 2.03 t plus 4.1. The velocity of y as a function of t, if I took the derivative of that, negative 0.544 t minus 1.1. And note, this should be important, if I take the derivative again, I get acceleration in the x direction of 2.03, which matches this. And if I take the acceleration in the y direction, if I take the derivative again, I get negative 0.544, which matches that. Okay? So look, all of our math is internally consistent. Woo! Okay. And then we can just plug in values at, 10 seconds and be good to go. So hopefully this kind of helps you understand the concept of what we're saying, where we're going to break things out into x and y components, kind of treat them separately. Now in this case, we kind of had like a constant acceleration that we broke into x and y components. What we're about to have in free fall is we do have acceleration this way, a equals yes, and lefty righty, since there's no gravity, there's going to be no acceleration. Okay, that's what we're going to do here in a second, just so you're prepared. But if you kind of are working your way through this, maybe you can start to think in that direction.